Have you ever stopped to think about what's really going on inside a sealed bottle of soda? Or how your own body, right now, is so incredibly good at moving oxygen around? Well, the answer to both lies in this powerful, universal concept called chemical equilibrium. It's this hidden force that's running the show all around us, from giant factories to the air we breathe. So let's dive in and see how it all works.
Right off the bat, this concept is running your life. Seriously, every single breath you take kicks off this delicate balancing act. The equilibrium between oxygen and this protein, hemoglobin in your blood, it's what makes sure oxygen gets picked up in your lungs and then dropped off exactly where it's needed, like your muscles. It's a perfect, life-sustaining chemical handshake, and it's happening trillions of times a day inside you. It's incredible.
Okay, let's bring it back down to earth with a more everyday puzzle. We've all seen this, right? That amazing fizz in a soda bottle is all about equilibrium. You've got carbon dioxide gas dissolved in the liquid, all held under pressure. As long as that cap is on tight, the system's in a happy balance. But the second you twist it open, that balance is shattered. What's going on there? Well, by the end of our little journey today, you're going to know exactly why. So here's the game plan. We'll start by really getting a feel for what this balancing act is all about. Then we'll look at the rules that control it and, this is the fun part, how we can actually push the system to get what we want. We'll also see how it works with acids and bases, and then we'll wrap it all up with why this stuff is so important to understand.
All right, let's get into the core idea. A lot of the time when we look at something in equilibrium, it seems, well, completely still, like nothing is happening at all. But I'm telling you, that's just an illusion. The reality is way, way more exciting.
So it's super important to get this straight. There are two kinds of balance. Static equilibrium is, well, static. It's a book on a table, nothing is moving. End of story. But chemical equilibrium is dynamic, and that means there is constant, frantic activity happening in both directions, but it's just so perfectly balanced that to our eyes, it looks like absolute stillness.
Let's look at the official definition for a sec. The crucial phrase here is rate of the forward reaction is equal to the rate of the reverse reaction. The reactions have not stopped. You've still got reactants turning into products, that's the forward reaction, and at the exact same time, you've got products turning back into reactants, that's the reverse. When the speeds of those two processes match perfectly, bam, you've hit dynamic equilibrium.
This might sound a little abstract, so here's a fantastic way to picture it. Imagine cylinder 1 is all your reactants, and cylinder 2 is your products. You start moving water from 1 to 2. As the level in 2 starts to rise, you begin moving some back to 1. Eventually, you'll hit this sweet spot where the amount of water going from 1 to 2 is exactly the same as the amount going from 2 to 1. The water levels will stop changing, even though you're still busy moving water back and forth. That is dynamic equilibrium in action.
So we get it. Equilibrium is this dynamic balance. But can we predict where that balance point is going to be? Is a reaction going to end up with mostly products, or is it going to hang back with the reactants? Turns out, chemistry has rules for that. It all comes down to one incredibly powerful number, the equilibrium constant, or Kc. Think of it like a personality score for a reaction. It's a simple ratio. You put the amount of products on top and the amount of reactants on the bottom. And what's so useful is that for any reaction at a certain temperature, this ratio is always a constant. It tells us the whole story of what that reaction naturally wants to do.
The size of this Kc number tells us everything we need to know. If Kc is a huge number, we're talking bigger than 1,000, it means the top part of that fraction, the products, is way, way bigger than the bottom part. The reaction basically goes in one direction, and that's it. Just look at the formation of HCl. Its Kc is a 4b with 31 zeros after it. That's insane. At equilibrium, you're going to find pretty much only product.
Now, if Kc is in this sort of middle zone, it tells a totally different story. It means that when you reach that balance point, you've got a healthy mix of everybody hanging out together, a good amount of reactants, and a good amount of products. Neither side is really winning. The reaction to make hydrogen iodide is a classic example of this. It's a true two-way street, a real dynamic balance.
And then, of course, you have the other extreme. What if Kc is a teeny tiny number? Well, that means the bottom of the fraction, the reactants, is huge compared to the products on top. This reaction barely gets off the couch. It just doesn't really want to happen. Look at the decomposition of water at this temperature. That Kc is so small it's hard to even imagine. The reaction just sits there.
Okay, so knowing the rules is one thing, but what if we don't like the outcome? What if we want to force a reaction to make more product than it naturally wants to? Well, this is where things get really interesting. This is where we learn how to become masters of equilibrium.
The key to controlling all of this is a brilliant idea called Le Chatelier's principle. And it's actually pretty simple. Think of a system in equilibrium as being lazy. It's comfortable. If you disturb it, if you poke it by changing the concentration, pressure, or temperature, it will do whatever it can to oppose what you just did and get back to a state of balance. It's basically a principle of chemical resistance.
And trust me, this isn't just some abstract theory. This has world-changing consequences. The Haber-Bosch process, which makes ammonia for fertilizer, is arguably one of the most important chemical reactions in human history, but its natural equilibrium point kind of stinks for production. So how do engineers use Le Chatelier's principle to squeeze out as much ammonia as possible and literally feed the world? It's an amazing story of chemical ingenuity.
They use a three-pronged attack. First, they crank up the pressure, a lot. See, you have 4 gas molecules on the left and only 2 on the right. By squeezing the system, it tries to relieve that pressure by shifting to the side with fewer gas molecules, making more ammonia. Second, the reaction releases heat, so they lower the temperature to sort of pull the reaction forward. And third, this part is just genius. They constantly remove the ammonia as it's being made. The lazy system feels that loss and tries to replace it, so it just keeps churning out more and more. It's an incredible application of this principle.
And if you want to see this principle with your own 2 eyes, this experiment is perfect. You've got 2 sealed tubes with the same gas mixture. The colorless gas N2O4 is in equilibrium with this brown gas NO2. Now watch. You stick one tube in an ice bath. To fight the cold, the system tries to generate its own heat, so it shifts in the heat-releasing direction, making more of the colorless gas. But in hot water, it does the opposite. It tries to cool itself down by shifting in the heat-absorbing direction, making more of that brown gas. It's such a simple, powerful visual proof of Le Chatelier's principle at work.
Okay, so this ability to push and pull a system isn't just for massive industrial plants. The exact same principles of equilibrium apply everywhere, even down to one of the most fundamental concepts in all of chemistry, the world of acids and bases. Because at its heart, it's just another dynamic balancing act.
The most useful way to think about acids and bases is the Brønsted-Lowry theory, and it is beautifully simple. An acid is a proton donor. A base is a proton acceptor. That's it. That's the whole game. Every acid-base reaction is just a game of catch with a tiny proton, and where that proton ends up is all decided by, you guessed it, equilibrium.
So how do we keep score in this proton passing game? That's where the pH scale comes in. It's really just a convenient way for us to talk about how many of those hydrogen ions are floating around in a solution. A low pH means lots of H+ ions, so it's acidic. A high pH means very few H+ ions, so it's basic.
And this scale is literally all around you. If you look at the chart, on the really acidic end, you've got things like stomach acid and lemon juice. Smack in the middle at a perfect neutral 7 is pure water. And then over on the basic side, you'll find things like washing soda and household cleaners. Every single one of these is just a different point of equilibrium for the concentration of protons.
Okay, so we've covered a lot of ground here, from fizzy drinks to feeding the world. Let's step back for a second and pull it all together. Why does this concept of chemical equilibrium really, truly matter?
First, and this is the big one, remember that equilibrium is dynamic. It's not dead, it's a constant balanced dance. Second, it's predictable. That Kc value tells us exactly where a reaction wants to settle. Third, and this is maybe the most powerful idea, it is controllable. The Chatelier's principle gives us the cheat codes to push and pull reactions in the direction we want. And finally, it is just absolutely everywhere.
At the end of the day, equilibrium is nature's ultimate balancing act, and you can see these same principles playing out all over the place. From economics to ecology, these ideas of a dynamic balance, of pushes and pulls and systems always trying to find stability. So I'll leave you with this. The next time you see something that looks perfectly still, ask yourself, what's the hidden balancing act that I'm not seeing?